Well, in this short video, we're going to go over how to identify what variables you want to solve for and what constants you want to use, and ultimately how to use the ideal gas law. So the ideal gas law is going to let us approximate some of the information about the variables that we've been discussing with gases and gas laws up to this point, right? With one caveat being that the ideal gas law is essentially an idealization, right? So it works well if we make a few assumptions about gases, and it works for some gases better than others. But we'll discuss that in the lecture. So for now, all you really need to know is that the conditions that would allow you to use the ideal gas law to make some approximations should be relatively low pressure and relatively high temperature, right? Outside of these conditions, the ideal gas law doesn't fit gases quite as well. And so, here is the ideal gas law, right? PV equals nRT, or PivNert. So we have pressure times volume equals N times R times T. And N here is the number of moles of gas we're discussing or examining. R is the gas law constant, and T is temperature in Kelvin. Remember, temperature always has to be in Kelvin when we're using these gas laws. So R, if you've never seen it before, is actually, it can be either of these two things that are essentially interchangeable if you convert between units, which is a little beyond what we're doing right now. But we're going to give you two values for the constant R that you can choose to use when you need to. So the first being R equals 0.08206, and the units on this are liters times atmosphere divided by moles times Kelvin. And the second value for R we're going to discuss and use is 8.314 kilopascals times liter divided by moles per Kelvin. And again, depending on what information you're given and what you're asked to solve, you have to pick which R suits your question. Again, knowing that technically these values are equal if you interchange and convert between units, right? The biggest difference here being atmospheres to kilopascals. So let's attempt to use the ideal gas law, right, PivNert, for our first question on the next slide. So for our first question here, we have 1.8 moles of helium being held at 418 Kelvin in a container with a volume of 6.2 liters volume, right? We want to know what the pressure is of this gas exerting in kilopascals. So up here, right, we've broken down all our variables. We have P, which we're trying to solve in kilopascals, volume 6.2 liters, number of moles 1.8 moles, our two R values, right, the first and the second, and then temperature 418 Kelvin. So for this question, we're being asked to solve for pressure in kilopascals. So of the two R values, we're going to pick the R value that has kilopascals in its units, so 8.314. Next, let's plug in these values, right? So we're going to have pressure, which is our unknown, times volume, 6.2 liters, equals 1.8 moles, times our R value, 8.314 kilopascals, times liter, over moles times Kelvin. Right? We're going to put that in parentheses. And then our last variable times temperature, which again is 418 Kelvin. So I'm going to go ahead here and immediately cross out some of our units, right? Moles cancel in the numerator denominator, so is Kelvin. And now we're going to divide each side by our volume, 6.2 liters. So over here on the left, that's going to cancel out once I cancel it out. 6.2 liters here. So because this is in the numerator, and this liter is also in the numerator, those units cancel out. And from there, we just multiply across and divide, leaving us with a final pressure of 1008.9 kilopascals. Excellent. Okay, so on to our second example here. So in this question, we have our question is how many moles of hydrogen gas are present if our sample is 27 degrees Celsius, is held in a 180 liter storage tank at 344.8 atmospheres. So note that this pressure is very high, quite high, right? So normally you might not be able to use this, use the ideal gas law, because again, we want very low pressures and very high temperatures. This is just for practice though, so we're going to use this information for now, but again, remember, when using the ideal gas law, we have to make a few assumptions, and if we were to use the ideal gas law outside of those assumptions, the ideal gas law may not actually accurately calculate some of the things we're trying to calculate. So let's start here, right? Again, we have Pivnert, P times V equals N times R times T. So we know our pressure is 344.8 atmospheres. We know that our volume is 180 liters. We are trying to solve for the number of moles, right, N. We have our two R values again, and we have a temperature of 27 degrees Celsius. So in this question, we're working with a pressure that's in units of atmosphere. So let me circle this R. We're going to use this R value because it has atmospheres in its units. And again, remember that all temperatures must be in Kelvin. So we're going to convert degrees Celsius into Kelvin by adding 273.15, which will give us a final temperature of 301.5 Kelvin. Right? From here, we just plug in the information that we have. So we're going to plug in pressure, 344.8 atmospheres, and our volume, so that's times 180 liters, equals N, the number of moles that we're trying to solve for, our value of R, so that's 0.08206, again, liters times atmospheres divided by moles times Kelvin. Close that off with parentheses, times 300.15 Kelvin. So immediately I'm going to cancel some units. Our Kelvins are going to cancel out. Next, we're going to divide both sides by 0.08206 along with the remaining units. And we're going to also divide this side by 300.15. Next, we'll divide the left by these as well. So it's 344.8 atmospheres times 180 liters divided by our R value with the remaining units and our numeric value for temperature minus the units because we've already canceled them out. So now we can cancel out some more units on the right and the left. So atmospheres in the numerator cancel out, liters in the atmosphere, or excuse me, liters in the numerator cancel out. And now, because moles are in the denominator of a denominator, that can actually get flipped to the numerator. And if we plug in chug here, we are left with 2,520 moles of hydrogen gas, right? Right around there. It actually rounds up to 2,500. And that's it. So those are some fairly simple ways to use the ideal gas law. Again, we need to make those assumptions: low pressure, high temperature. And I had the periodic table in a few of my slides because we're going to discuss what makes an ideal gas an ideal gas. And in subsequent lectures, we're going to actually talk about deviations from the standard gas law, or excuse me, the ideal gas law, and some of the assumptions we need to make for a gas to be ideal in the first place. So email me with questions. Otherwise, I will see you next class.